We'll continue Model 5 Design of Control System. Consider the example. The system shown in figure. Determine the damping factor and natural frequency of oscillations for k is equal to 15. Also determine the steady state error for unit ramp input. Determine the derivative feedback constant Kt which increases the damping ratio of the system to 0.7. What is the steady state error to unit ramp input with this setting of derivative feedback constant? Find the suitable values parameters k and kt so that damping ratio is increased to 0.8 with the steady state error as obtained in part A. So diagram is given. The solution is, in the absence of derivative feedback, g of s is 15 divided by s into s plus 3, h of s is equal to 1. The closed loop transfer function is c of s by r of s is equal to g of s divided by 1 plus g of s into h of s. So after substituting the values, we'll get it as 15 divided by s square plus 3s plus 15. So characteristic equation is s square plus 3s plus 15 is equal to 0. Comparing with the second order equation, that is omega is equal to square root of 15, it is 3.87, and zeta is equal to 3 by 2 omega n, that is 0.387. Velocity error constant kv is equal to limit of s tends to 0 s into g of s. Kv is equal to limit of s tends to 0 s into 15 divided by s into s plus 3 is equal to 5. ESS is equal to 1 by kv, 1 by 5 is equal to 0.2. With the derivative feedback control, g of s is equal to 15 into 1 by s into s plus 3 divided by 1 plus kas divided by s into s plus 3. So g of s is 15 divided by s square plus ki plus 3 into s. So c of s by r of s is 15 divided by s square plus 3 plus ki into s plus 15. Omega n is square root of 15, 3.87, and 2 zeta omega n is equal to 3 plus ki, and ki is 2.422. So g of s is 15 divided by s square plus 5.422 s. Kv is equal to limit of s tends to 0, g of s, s into g of s. Kv is equal to limit of s tends to 0, s into 15 divided by s into s plus 5.422, that is 2.76. ESS is equal to 1 by kv, 0.3615. Find the suitable values of the parameter Ka and Kt so that damping ratio is increased by 0.8 with the steady state error as obtained in part A. C of s by r of s is equal to Ka divided by s square plus 3 plus Ka into s plus Ka. Omega n is equal to square root of Ka. 2 zeta omega n is equal to 3 plus Ki. 2 into 0.8 into square root of Ka is equal to 3 plus Ki. G of s is equal to Ka divided by s into s plus 3 plus Ki. Kv is equal to limit of s tends to 0, s into g of s. Kv is equal to limit of s tends to 0, s into Ka divided by s into s plus 3 plus Ki. Ka divided by 3 plus Ki. ESS is equal to 1 by Kv, 3 plus Ki divided by Ka is equal to 0.2. 0.2 Ka is equal to 3 plus Ki is equal to 2 into 0.8 into square root of Ka. So Ka value is 64 and Ka value is 9.8. Proportional plus integral controller, PI controller. In this control, the actuating signal consists of proportional error signal added with integral error signal, that is ei of t is equal to e of t plus ki integration of e of t into dt. Taking the Laplace transform, ei of s is equal to e of s plus ki e of s divided by s. C of s by r of s is equal to 1 plus ki omega n square divided by s cube plus 2 zeta omega n square plus omega n square plus ki omega n square. So s cube plus 2 zeta omega n square plus omega n square into s plus ki into omega n square is equal to 0 is the characteristic equation. So we know that E of s by R of s is equal to 1 by 1 plus G of s into H of s. So G of s is s plus ki omega n square divided by s square s plus 2 zeta omega n, and H of s is equal to 1. So therefore E of s by R of s is equal to 1 divided by 1 plus s plus ki omega n square divided by s square s plus 2 zeta omega n. EFS by RFS is equal to S square S plus 2 zeta omega n divided by S cube plus 2 zeta omega n S square plus omega n square S plus Ki omega n square. EFS is equal to RFS S square S plus 2 zeta omega n S cube plus 2 zeta omega n S square plus omega n square plus Ki omega n square. For the ramp input, RFS is equal to 1 by S square. So ESS is equal to limit of S tends to 0 S into EFS. If you substitute the limit, the ESS value will be 0. For a system without integral controller, the steady state error for the ramp input is 2 zeta divided by omega n. For a system with the integral controller, the steady state error ramp input for is 0. Thus, the integral controller improves the steady state performance, but it may lead to oscillatory response. Proportional plus integral plus derivative controller, that is PID controller. The actuating signal consists of proportional error signal added with integral and derivative of error control. EA of t is equal to E of t plus KD dE of t divided by dt plus Ki integral of E of t into dt. So you take in the Laplace transform, EI of S is equal to E of S plus KD S into E of S plus Ki E of S divided by S. Taking the common factor, E of S is equal to 1 plus KDS plus Ki by S into E of S. Next topic is compensators. Compensators are the subsystems introduced into the system to meet the design specifications. The desired behavior of the system is specified in terms of transient measures and the steady state error. Compensation may be cascaded or feedback. So compensators are of three types: lead compensator, lag compensators, lead lag compensators. Compensators. First one, lead network. If a sinusoidal input is applied to the input of a network and the steady state output as a phase lead, then the network is a lead network. Lag network, if the steady state output as a phase lag, then the network is called as a lag network. Lag lead network. In a lag lead network, both phase lag and the phase lead occur in the output but in different frequency regions. Phase lag occurs in the low frequency region and the phase lead occurs in the high frequency region. Lag compensator. Lag compensators have a transfer function of the form Gc of S is equal to S plus Zc divided by S plus Pc. 1 Sc plus 1 by tau by S plus 1 by beta tau. Beta is equal to Zc divided by Pc greater than 1 where tau is greater than 0. Pole is located to the right of 0. So lead compensators improves the steady state behavior and preserves a transient response. Lag lead compensator. Lag lead compensators have a transfer function of the form Gc of S is equal to S plus Zc1 divided by S plus Pc1. S plus Zc2 divided by S plus Pc2. So Gc of S is equal to 1 plus 1 by tau 1 divided by 1 plus 1 by alpha tau 1 into 1 plus 1 by tau 2 divided by S plus 1 by beta tau 2, where alpha is equal to Zc1 divided by Pc1 is less than 1 and beta is equal to Zt2 by Pc2 is greater than 1. Tau 1 is greater than 0 and tau 2 is also greater than 0. Lag lead compensator is a combination of lag compensator and lead compensators connected in series.